Hi everybody. Where we left off last time, we were doing this Monty Hall game. We were playing this game where we click on a door, we are shown a goat, and then we have to decide whether to stay or switch. Pick one. Stay. Okay? Switch or stay? Switch. Okay, and so forth. So if you play this game a lot, here are some statistics that were compiled while I was waiting for the announcement, which is that when I tried to stay over and over, I lost 80% of the time. But when I switched, I won 82% of the time. Now, maybe I was just lucky with my switches and less lucky with my not switches, but it seemed like in this particular experiment, switching seemed to be good. So let's talk about this problem in some more detail. Okay, so many of you have seen this before. Actually, I was surprised last time I did this lecture that I think 80% of students had previously seen it or something. A lot from YouTube videos or, Veritasium or whoever. And so if the question is, should you switch doors? If you've never seen this before, it's a little shocking that the answer is actually yes. Like, switching is actually better. And when I first learned about this as an undergraduate at a time when the internet couldn't pollute me with the secret information, I was amazed and disturbed. And all of us are a little mad that this was true. So let's talk about why it is true that switching is better, which is going to lead us into what we'll talk about today, which is conditional probability. So here's the shortest explanation. And if you've never seen this, I don't think I'll convince you now, but you'll have to think about it more later. But I think you'll agree with me that your chance of being right in the first place was 1/3, right? Because you picked a door and the car was randomly behind one of those three doors, so there it goes. So only two possibilities exist. One is that you were right with probability 1/3, and the other is that you were wrong with probability 2/3. So this is the one you picked, and this is these are the other 2/3 probabilities. Okay. So suppose the host opens door number 3. How do the probabilities change? Well, the chance the original choice doesn't change retroactively in time. It's still a 33% chance that you were right the first time, right? I mean, that didn't change what happened before. However, we now know that the probability that the car is behind this door is 0. Okay? So where did this probability go? Well, it had to be there. It has to be behind door number 2 with 2/3 chance. So door 3 cannot have the car because there's a goat. So that means this one's actually 2/3. So it's actually better to switch because you gained information about what was behind the other 2 doors, specifically that this was a goat and not a car. So you should switch. That's the short version of it. So basically, after opening a door, the chance you were right is still 1/3. So switching to the other one must have a probability of 2/3. And you can think about this more formally in terms of conditional probability, which we'll spend most of today talking about. But that's the short argument that maybe I've convinced you. Now, when this problem was actually first put out there, if you've never seen this and you're like, I just still don't believe you, you're in good company. When this problem was answered in Parade magazine by a columnist who was very smart and had lots of things to say, the answer had just lots of angry mail. So I'm going to show you what that was like when this happened in the 1990s. I think I just said in 1990, yes. Okay, so here we go. Someone asked this question. Marilyn responds, yes, you should switch. And so you go. And everyone starts replying, you blew it, and you blew it big. You blew it big. Since you seem to have difficulty grasping the basic principle at work, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There's enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame, PhD. Your answer to the question is in error. But if it is any consolation, many of my academic colleagues have also been stumped by this problem. And it goes on, and it's kind of a fun read of people being very, very mad about this in the year 1990. But now we have YouTube and 3-hour podcasts, and you can learn more things these days. All right, so you might find that fun to read later. Okay. There's another way to think about this problem, which is annoying. And I'm going to show it to you because I want to show the universality of this sample space approach, this idea that we're drawing samples from a space. And this will give you a sense of how we can contort and solve different problems than just our counting problems. Okay? So we can also think about the Monty Hall problem in terms of a sample space where we draw 3 samples from the set 1, 2, 3. Okay, what do they mean? Well, the first thing that's drawn is the door that has the car, and that's randomly chosen, let's say, by the TV show crew. Okay, so I'm assuming they pick randomly. Then you pick a door, and I'm again going to model it as a random selection. So they pick a number 1 through 3. Then you pick a number 1 through 3. And then K, that's the door the host opens that always has a ghost. So the host will randomly pick a door, but there's restrictions on what they can do. They will never select the door with the car, and they will never select the door chosen by you. They're not going to open the door that you picked, and they're never going to show you the car and then give you the option to switch. Okay? So then questions. What's the cardinality of the set we're drawing from? How many samples are we drawing? Are we drawing with or without replacement? And what's the cardinality of the sample space? I'm just going to answer these for you. So the cardinality is just 3. Those are the 3 different things I can draw. How many samples are we drawing? 3. Are we drawing with or without replacement? It's kind of a mess. If we compare I and J, actually I'll just go straight to my slides. I would say it's neither with or without replacement. I'll say J is with replacement. Why? Why is J with replacement relative to I? Yeah? You could choose the right answer, but K is drawn without replacement. It will not draw either I or J. So it's an interesting drawing problem. You can draw the same thing, but the host is never going to draw either I or J. And then what's the cardinality? Let's look at that on the next slide. So the sample space looks like this. There's 3 repeat draws. There's a 1/3 chance that the actual car is behind door 1, door 2, door 3. And then we draw more samples. What's this one? That's the door you pick. Okay, so there's a 1/3 chance that they picked 1, and there's a 1/3 chance you pick 1. Okay? Now it gets a little more interesting. If the car is actually behind door 1, and you pick door 3, what door could the host pick? Are there multiple choices? Just one? Just one. Which is, which door? 2. Yeah, so door 2 is the only one that will get picked with 100% probability. So in terms of sample space, the first draw, there was a 1/3 chance that the car was put behind door 1, a 1/3 chance that you picked door 3, and then at that point there's a 100% chance that the final draw is a 2 because it's without replacement. Okay? Happy with that? Now this still doesn't tell you what the right strategy is, but this is just showcasing the sample space. Okay, what about here? If you picked 1, or they picked 1 and you picked 2, then the host will pick 3. How about here? If the car is behind door 1 and you picked door 1, what can the host show you? Either one, 2 or 3, with what probabilities? Yes, 1/18 overall, or I would say 50% for each of these edges. So I think 1/18 is a good answer, so is 1/2. Okay? So we think of these as different things that could happen. These 2 possibilities happen 1/9 of the time, and these 2 happen 1/18 of the time. Okay, so there's some asymmetry here. Like the asymmetry that the angry readers were not perceiving is this, that some of these actual combinations, if you think about it as a drawing I, then J, then K, they happen with different chances. And again, modeling my choice and everyone's choices is random. Okay? Then we can continue the same process. We can do the same old thing. So again, the reason there's 2 different choices here is because I picked the correct door, so the host has 2 different wrong choices to showcase. And then likewise, I have up here. Okay? So that's the whole sample space of what can occur, but this still doesn't tell you the right strategy. This just says what could happen. So now we need to consider what I'll call the final and deterministic step, which is our strategy. So basically, I get to this point, 3, and I can decide to either keep my choice. What was my choice here? 1. So I could either keep 1, or I could switch to 2. Either one of those is possible. I can't switch to 3 because there's a goat there. I'm not going to do that, okay? So I'm going to show you the not switching strategy. If I don't switch, then I'm keeping the 1. And was that correct? Yes, because that's where they put the car, right? That's why I made it gold to say, good choice. Okay, how about here? Here, what was my choice? 1, and is that the right choice? Yes, it's still right. Okay, these are both good. Okay, here, what was my choice? 2. And what will I do? Let's see. If I do not switch, then what choice is going to be here? We're not switching. So there's also going to be a 2, because I'm not switching, right? All I'm doing is copying and pasting the circular bubble here. That's my earlier choice. And this is going to be here. And this time it's wrong, right? The actual car was in door 1. I picked 2, so I'm wrong. Does not get the gold color. And if you would like, you can repeat this process over and over and over and over, coloring in all the possibilities, and you can see the following. If I don't switch, these are all of the winning examples right here, all the winning draws. If you add up their probability, they're 1/3, right? All of the weight of those outcomes, these gold ones where I don't change my choice, has only a 1/3 chance of happening, okay? By contrast, if I switch, I'm going to get the opposite diagram basically here. So here, let's do one out loud just in case you're a little lost. In this particular case, what did I choose? Like, what was my choice along this path? 3. I picked 3. So they picked door 2. I picked door 3. And I'm going to switch now. So what am I going to switch to if they showed me 1 and I previously had chosen 3? 2. And is that correct? Yes. Okay, so that's why this is a gold 2. It's the other choice than 3. It's 2. And the reason it's gold is because the choice matches this box, which is the true answer. Okay, and I just ripped through that pretty quickly because I don't want to belabor this too much. But the point is that if I add up all of these outcomes, the gold outcomes, in the switching strategy, then it's 2/3. Okay, so this is a different way to prove this that if you're me and you've prepared this lecture is very crystal clear, but for you it's a lot to think about in a short order. So if you'd like, this is a less intuitive answer, a lot more to think about, but it's more, I guess, direct in terms of what we covered in the previous lecture, the sample space approach. In other words, I gave you 2 arguments. One was this 2/3 needs to get moved somewhere, or this 1/3 probability needs to get moved somewhere. I think that first argument's fairly clear, though makes me nervous if I hadn't heard it before, and that involves the idea of conditional probability. And then we had this more painful second argument, basically to showcase sample spaces. Any questions about this? Okay. Yeah. Yes. Why does it? Well, because the universe. What's a nice, clean answer to that? Because it's the question is whether or not you were right in the first place, I guess. And whereas in poker, there's like a dynamic world state that's evolving all at once, is my short, boring answer. Manuel? Yeah, oh, did you have a question too? Oh, no. Okay. Ha, good. Okay, I hope the answer is satisfactory. If not, I'll think about it and see if I have a better, cooler answer. Okay, let's do our next set of notes. So the lectures, this lecture is going to cover part of the next set of notes. We're not going to get through all of the notes, but the next set of notes is a little shorter. So again, there's going to be a little overlap between this lecture. So this set of slides is going to cover part of the next set of notes, and then we'll wrap it up in the next one. All right. So as the motivating example for conditional probability to showcase a new type of problem we can solve, I guess Monty Hall is another example, but this is a cleaner and less controversial problem, is that problem I gave in the first lecture on Tuesday for this segment of the course, which is, imagine we have 2 different shopping centers we select randomly, and then we select a restaurant randomly from among those restaurants at that shopping center. If we were to ask something like, let's suppose we pick one of these shopping centers randomly with 50-50 chance, and then we pick a restaurant with equal probability among the choices, we can start asking kind of reverse questions. So, for example, if I say, if we ate at a Moroccan restaurant, what is the chance that we picked center 1? That's a question we might try and solve. Okay? I'll give you a bad solution, which is to say, I think it's 2/3, because 2/3 of the Moroccan restaurants are in center 1, right? So if I picked a red one, yeah, then probably I went to center 1, because that's where a lot of the red items are. But the real answer, strangely, is 44.4%, 4/9. And we'll come back to this problem later, and I'm going to give you the machinery to reason about this kind of problem. I guess it's a reverse probability problem, I might call it. Okay? All right? And so to get there, I'm going to start by outlining some key definitions. There's going to be this definition called 14.1 that's super important. And I'm going to walk through it a little slower than the notes because I want to make sure that the underlying ideas make sense and we're not focusing too much on the little symbols we write on the page. So let's suppose we have 4 3-sided dice, which you can actually purchase. This is what they've looked like. I've never seen one. But if we have 4 3-sided dice, we roll them. I want to know what's the chance we get 1, 1, 3, 1 as my roll, and we are going to take into account order. I should note that the notes talk about this as a balls and bins problem, but I like it better as dice because these just make natural sense. Okay. So this is just our usual sample space CP1 where the order matters with replacement. And the probability space is uniform, right? There's these 3 different choices that we can make 4 times. So it's going to be 3 to the 4th or 1/81st. That's the chance we get the specific roll 1, 1, 3, 1. Okay? No surprises there. What gets more interesting is when we start thinking about conditional probabilities. But before we do that, one more warm-up is let's talk about the chance of an event. So let's say that B is the event where we get no 2s. Okay? So I want to know, what is the probability of B? What's the chance that we get no 2s? That was the balls and bins problem that we did in the previous lecture. So we say, okay, well, all we got to do is count B, like the cardinality of B, and then divide it by the cardinality of the entire sample space. We did that before. This is a uniform probability space, so we could just take cardinality of B over cardinality of the entire sample space, and we're good. What is the number of different ways we can have no 2s? Well, that's just 2 to the 4th, because if we can only get 1s or 3s, we only have a binary choice. So we make 4 binary choices, 1 or 3, 1 or 3, 1 or 3, 1 or 3, and that gives us these 16 possibilities. So in other words, the chance that we get no 2s is the chance that if we think about it as one single draw out of a bucket of 81 possibilities, and only 16 of them have no 2s, then our chance is going to be 16/81st. Okay? So the probability of getting no 2s is 16/81st because the number of different ways to get no 2s is 16, and the number of ways to get anything is 81. Okay? All right. Now I have one for you. So let's suppose we already know that there are no 2s. That is, the event B happened. We know that fact. Okay? What's the chance that we rolled 1, 1, 3, 1? And I'll let you think about this for a minute. So I'm just guaranteeing to you there are no 2s. Okay? What's the chance that 1, 1, 3, 1 was our roll? Yeah, we knew it. I'm just telling you. Yeah. If we knew if I guarantee you that the roll that you got, like you roll the dice, and you can't see what they were, and I say, hey, there's no 2s. Now tell me what the chance is given that extra piece of information. Okay, so the way I like to think about this is how many different things can happen? Like if I told you that B occurred, how many different outcomes are possible? 16. There's only these. You don't get to pick from the entire space. You only get to pick one of these 16. And this is a uniform probability space, so it has to be just 1/16. We're not picking from the entire set of things that could happen. I gave you extra information. I told you there are no 2s. And if that's the case, you're only drawing from this set. Okay, so it's basically I'm redefining the problem. I'm saying you're rolling dice and there's no 2. Okay, this is all you get. Yeah.
The order matters. Like dice.
Yeah, here I'm saying the order. I'm considering the order of the dice. Yes. Yeah. Because it keeps things simple. Then you don't have to think like, oh, how many different ways are there to get something? Yeah. Okay. So this is known as conditional probability. It tells you the probability of an outcome given that we know some event happened. And the standard notation looks like this. We say the probability of this outcome given B, and the bar means given that. And it's an interesting piece of notation. I feel like students kind of memorize these different ways to like do algebra on these little symbols. I don't know, maybe I'll talk about this in a future lecture. But what I'm going to try and emphasize in this lecture is what's really happening under the hood with this. This is basically saying you are only drawing from this set, not the whole space. This is what you get to go from. Okay? So the probability of omega, or the sample point being 1131, or the outcome being 1131, is going to be 1/16. Okay? The rest of the space is irrelevant in this case. Okay. Now, let's think more carefully about conditional probability. Let's suppose the dice are loaded so that 1 comes up half the time and 2 and 3 occur 25% of the time. And there's no B anymore. I've gotten rid of the event B. Notice that. I'm back to the simple version where there's no events. Okay, so there's no conditional here. So there's this, I don't know why this title, this shouldn't say new idea conditional probability, because this is actually not conditional probability. So what is the probability that we get 1131 with loaded dice? Well, I'm just going to spoil this one because it's the same pattern as before. So there's 1, the chance that we get 1131 is the chance that we roll a 1, which is a half, times the chance we roll a 1, which is a half, times the chance we roll a 3 next, which is a quarter, which is times the chance we roll a 1 next, which is a half again. And so the overall chance of getting specifically this sequence, 1, 1, 3, 1, is 1/32. Okay? And again, this is taking into account order. So 1131 is distinct from 3111. So I'm only thinking about literally, I got a 1 on the first die, a 1 on the second die, a 3 on the next die, and a 1 on the fourth die. Okay? So hopefully that's not controversial. But now what's interesting is if I have to think about, okay, now I'm going to get complicated. I'm going to say, there are no 2s. So we're actually adding the extra layer of complexity. There are no 2s. That's guaranteed. What's the chance we got 1131? Okay, how would we do that? Okay? This, I think, is the most interesting and foundational definition in the lecture. And I'm going to derive the usual way of thinking about this rather than just giving it to you. And I'll first say it is incorrect to just do the same thing. We can't just say the probability is just what we got 1/32. That doesn't make sense. That was the probability if we got to pick any combination of dice rolls, but we aren't. We're only allowed to pick combinations that have no 2s. That's important. There are no 2s. So 1/32 only true if we're able to get any roll. But now I'm saying, you rolled the dice and there were no 2s. You have to think more carefully. Okay? So how do we do that? So what should we do? Any thoughts about this? Like intuitions? I guess I have a question for you. If we were to compute this sum here, like we add up the probabilities of every sample, omega, in B, if we knew that B was true. Okay, so we add all these up. What should that probability be? If you had to guess. Close. Not that either. I'll tell you. So if we compute this sum, we should get 1. That is, if we add up all the conditional probabilities, we should get 1. And the reason is there's 16 different things that could happen. And so we add up all of those probabilities of each of the different things that could happen in this universe of only 16 choices. Those probabilities should add up to 1. That's going to be our hint. Okay? So these conditional probabilities, whatever they are, they tell us, given that B is true, what's the chance we get a specific outcome? These probabilities should add up to 1. But that thing you were saying about adding up to B is interesting. So let's think about the following. So here's all the outcomes in B. I've typeset them for you, somewhat painstakingly. And I'm pretty sure there's no error, so let's cross our fingers. So here's all the things that could happen that are in B. There's no 2s. How many different ways are there? There's 16 of them, and here they are. And what's the chance of each of them unconditionally? Well, the chance of getting 1, then 1, then 1, then 1 is half to the fourth. The chance of getting 1, 1, 1, 3 is half to the third times 1 to the 1/4. And so forth. And those are all the probabilities of all these outcomes. Okay? If I simplify these, if I multiply this stuff out, you get these numbers. Okay, so that's all the outcomes in B if you don't want to have them as fractions. And that's how much, that's the chance of getting each of them. That's unconditionally. Okay? Now, how do we rescale these probabilities? Like if I want them to sum to 1. Maybe you weren't totally convinced by my argument earlier. But let's suppose that I wanted them to sum to 1. How would I rescale them? Yeah? Yes, right. We would divide by the probability of B itself, or in other words, we would divide by their sum. Like if I want these numbers to all add up to 1, then what I can do is just compute their sum and then divide everything by that sum. So in other words, to go from the unconditional probability, omega, these are all uncontroversial, to the conditional probability on B, I want them to sum to 1. So to get that, I divide everything by Z, which is the sum of all the original probabilities. And then I guess the question is, what is Z? Like, what is Z? I guess you just said it. Like, what is the sum of the original probabilities? That's just the probability of B, okay? Hopefully that's satisfactory. It made sense to me when I wrote it, okay? So in other words, if I take all the original probabilities and I divide them by the probability of B, I'll have another slide that maybe will convince you if you're not happy with this argument so far. If I divide all these probabilities, all these P of B's, then I will get the conditional probability. And by the way, the probability of B is 81/256. That's just some number I came up with earlier. Okay, that's what the sum of these original numbers. Let me go back here. The sum of all these numbers here is 81/256. Okay? In other words, the probability you get no 2's is 81/256. If I want the conditional probabilities, I divide by that B, and I end up with these numbers. And these numbers add up to 1. Okay? Why is it important? Back to the question I raised earlier. Why is it important that the conditional probability sum to 1? It's because I'm saying, hey, you need to pick one of these outcomes from B. Like, these are your only choices. And if these are your only 16 choices, the probability you get any specific choice, all those probabilities need to add to 1. Okay? Right? So that's the idea. We can't just keep the original probabilities when we condition on B. We need to rescale. Do I have that other slide maybe hidden right here? It'll be in one slide. Okay. All right. I'm going to present this in a slightly different way in a moment. I'm going to unhide the slide. So I don't think that came out as clear as I was hoping, but I have a shorter version. So what we just basically showed is that if omega is in the event B, it is always the case that the conditional probability of an outcome, knowing that B is true, is just the unconditional probability divided by the probability of that event. If omega is not in B, like that is, imagine omega is like 2, 1, 2, 2. What's the probability of getting 2, 1, 2, 2 if we know there's no 2's? 0. Okay. Let me reframe that a little, because I don't know that it really came across so beautifully. Okay. So we know that the conditional probabilities must sum to 1. In other words, if I tell you you are picking a sample from B, what's the probability of each omega given that B? You know that those probabilities must sum to 1. Here they actually are. Here's the real answers. These things must sum to 1 because these are the only 16 things that can happen. If you were to, so we know that it's true that if we were to sum all these conditional probabilities, it must be 1. Let's imagine we were lazy and we did not rescale. We just said the probability of omega given that B is true is just the probability of omega. If you sum them all up, you would get P of B, right? But that doesn't match what we said. This is a contradiction. We said the individual conditional probabilities have to be 1, but here we got B. So how do we fix that? Well, we have to divide the individual probabilities by B. This is the more abstract argument that also helps. Okay, so any questions about that? I feel like I lost some of you guys there, but I'll disentangle if I can. Yeah. Right, it's any, so you can think about, you can substitute any specific omega, yeah. So one example of an omega would be 1131, yeah. Make sense? Right. So if omega includes 2 and our event does not, right. So this is the caveat here. Right. So if omega is not in B, then the probability has to be 0. Yeah. Right. It's a conditional equation. Yeah. If omega is in B, this is the case. Otherwise, this is true. Yeah. Yeah. Good question.
Is it accurate to say that once we know that B is true, that means we've expanded the probability space so that we know that the sum of all outcomes has to be within that red blob earlier, but the ratios between those particular probabilities still
Right. The ratios, so whenever you say B is true, I would say I contract the universe. I'm only thinking about a sub-universe. And then we need to basically scale, all those probabilities still need to be relatively equal within that event, but we need to scale them up so that they sum to 1. Yeah. Yeah. Yeah, we'll have intersections shortly. That's coming soon. Don't worry. So I'm only showing the probability, the conditional probability of an outcome given an event. Soon I'll talk about the probability of an event given an event. Okay? All right. So this might be one of those things where going through it in so much detail actually made it more obscure. I hope not. All right. So let's consider now an event conditioned on an event. In this case, I'm going to imagine an event which is that we roll at least 3 ones. And this is unconditional. Okay, there's no extra constraint. I'm not whispering some secret about what your result was. I'm just saying you rolled these 4 3-sided dice. What is the probability that we get at least 3 ones? Okay, well, that's just going to be the following. I'm going to spoil this one for you. There's the chance that we get 3 ones. So these are all the different ways to get 3 ones. You could have 2 then 3 ones, right? Or basically, it's 1, 2, and 3 ones, or 1, 3, and 3 ones. Or you could get all 4 ones. So the overall chance of getting at least 3 ones is 9/81. Hopefully you agree with me. I can say the size of the event A is 9. And because the probability space is uniform, that means the probability of this event is just how much of the sample space is covered by this event. Okay. Now let's ask the question, well, what's the probability of A, that we get at least 3 ones, given that there are no 2s? Okay? So this is a good place, if you're watching this on the internet, to pause and try and figure out where I'm going to go. But this is the idea. I have this event B, I have this event A, and there's some events in common, and there's some things that are only in B and some things that are in A. And I haven't said anything about their intersection as yet. But these are just 2 events in space that do intersect. If you think hard, you can see that they intersect. Okay? So what's the actual probability going to be? Well, I know that the probability of an event is just the sum of the probabilities of the different individual outcomes in that set. Remember, an event is just a set of outcomes. So the probability of an event is just the sum of the probabilities of the individual outcomes that comprise that set. So here it is. The probability of the event A is just the sum of the individual probabilities that for each outcome in the event A, conditioned on B. So for example, the probability of A given B is the probability you get this one conditioned on B, plus the probability you get this one conditioned on B, and so forth. So you're just adding up the conditional probability of these 9 different things on B. Okay, so what are these 2 values, for example? So I gave you the sum. It's just the sum of the conditional probabilities of these 9 samples. Tell me what these 2 are. And this is our second of 5 such questions today. And B is again the event from before where we roll no 2s. I'm still going to wait for more answers on this one. And you can feel free to chat. Okay. we're in pretty good shape. So this one right here, this probability, if we know there's no 2's, what's the probability we get this roll? 0. That one seems pretty good. This one, we were 70% correct, that it was 1/16. And the argument here is don't overthink it. Basically, B consists of 16 different samples, right? So 16 different things that could happen. So it's simply, what is the probability you get 1, 1, 1, 1 if you know that B is true? There's 16 things here. A is irrelevant to this calculation. So if you're up here thinking about A, you've overthought it. And the answer is simply that there's 16 things that could happen in B, and this is one of those 16 things. Okay? All right. So if that's true, if this right here, if the probability of this is 0 and the probability of this is 1/16, what is the overall probability of A given B? In other words, if we add up each of these probabilities, you just figured out these are all 0, and this one's 1/16. What's the probability if we add all of them going to be? 5/16, right? That's because there's basically only 5 of these elements. See, I've made them purple now. Only 5 of those elements from A are also in B. Okay, so in other words, we're adding up these 5 events here. Okay, so these are all the things that could have, we want to add weight to this expression, but these are all 0, and these are all 1/16. Okay? Subtle, but important to understand this. Okay? All right. So any questions about why this is 5/16? Yeah. Well, here this is all counting problem 1. We're counting the order, and we're doing it with replacement. Yeah. So we don't need to think about how many different ways there are to get like 3, 1. Oh, I see. So are you saying like how would we count this right here? Yeah. Ah, right. That would be counting. Oh, in fact, I have a typo here. This should be 1, 1, 3, 1. You guys spotted that perhaps. Then in that case, we would be picking the number of positions for our 1, 3 out of 4. So it'd be 4, choose 1. Yeah, and there's 4 of these right here. Yeah.
No, like if you wanted to get like both the 2 and
oh, this right here?
The initial 8, yeah.
Ah, the initial 8. So what do we need to think? I don't want to reduce. I'll think about it. What is it? I think it's 4 choose 1 times 2 because there's 2 different things that can go there. Is the boring answer. Yeah, that's the way I'm seeing it. Maybe there's a slightly more general pattern that I'm not perceiving, but yeah. Okay. Here's a more challenging one where I want you to dig into this notation. Okay, so it is true that the probability of the event A given B is the sum of the probabilities of every outcome that belongs to this event A conditioned on B. Which of these 3 other statements is also true? And tell me all of them that apply. There may only be one. Maybe there's 2. Could even be all 3. May as well stretch your brain in the middle of a lecture, right? Oh, there's one extra answer on there. Oopsie. I think. Oh, no, I got it. Okay. And if you're watching this on the internet, really think about this one. You can actually compute the exact values for these top 2 things as a hint to you internet viewers. Okay? So let's talk about these answers. All right, these first 2, those don't work because they're just 1. Let's talk about why they're just 1. This top one's 1 because we're adding up the probability of all of the outcomes in B, condition that we're in B. We already know that should add to 1. In fact, that's how we did the derivation earlier for our whole notation. So if you add up the probabilities of everything in here, you're going to get 1. How about if you add up all the omegas in A and B conditioned on B? Well, what's the probability of this right here, where my mouse cursor is, conditioned on B? 0. Can't be that. So this is also just 1. You're like adding a bunch of things that have probability up to 1, and then you're adding all this extra stuff here that has probability 0 conditioned on B. Lastly, this last one is actually also true. Maybe a better question is this, yeah, go ahead. It wouldn't be more than 1 because these points right here, like give me an example. So you won't double count these. Was that what you're thinking? Because when we do A union B, the union of the set doesn't create duplicates. But that's a good thought, right? Yeah. If the union operation had the property that it added a copy, like it formed a multi-set, then absolutely, I guess you would have a more than 1. And then in the intersection, I mean, yes, in that case, this expression here, we can also write it as we're summing only over this intersection here. Okay. So we could sum over A. That's fine. Or we could sum over the intersection, and both are fine. And the reason that it works whether you sum over all of A or if you sum only over the purple region is that all of these points here have probability what? 0, right there. So the probability of an event that is an A but not B conditioned on B is 0. Okay? All right. So we don't, like, it's optional basically to add in these probabilities because they all have probability 0. So you can write it this way, but this is a little more standard. But we're still not quite there. But I'm basically getting us to the formula definition 14.1. Okay? Yeah. Yeah. Mm-hmm. The total sample space? Oh, so the reason is that you basically are imagining, like, you zoom in and you look at this point and you say, hey, what's your probability? So what's the probability of this condition on B? 0, right. So you're going to every point in the space and asking, what's your probability, and adding those up. And basically the only things you end up adding are all of these, which are 0, then all the purple, and also all of the red. So all of this gets summed, and that's going to be 1.
But that just tells us that the total omega that's flow is 16, right?
Is 16.
Sample space is still 20, so shouldn't it be 3, 4?
Why are you saying 20?
Because it's A and B.
This is union. Oh, I see.
I'm rather A union B.
Well, I wouldn't think about A union B. It's like the union of these two things. I don't think I quite follow when you say 20.
Well, I mean the total possible outcomes in the sample space should be 20, right?
The
16 outcomes.
That's the span of omega. It's not what the actual probabilities are.
You understood the question. I didn't. So I'll let you guys talk after because I didn't quite follow the question. Okay. All right. So we're still not quite to the standard notation. So I'm going to do a little more algebra. And I'm going to say this expression's fine, but I'm going to manipulate it slightly. And I'm going to say we know that the conditional probability of a specific outcome is just the outcome probability divided by the probability of the event. This is what we did earlier, right? We said we have to rescale the probabilities. So if I want to be more explicit about what I'm doing, I take the original unconditional probability, divide by the event probability. And then here, this is just a constant, like P of B. It doesn't depend on omega, so I'm going to pull that out. And this is going to be the numerator. So all I've done is just pulled this constant out. And then at that point, I realized that this right here, if I'm looking at the probability of omega over this set, remember the union of two sets is just a set. I'm basically asking, try again. A and B are both sets, events and sets, those are synonyms. If I form the union of two sets, then I'm also forming a new event. So it's just the probability of an event, right? Like just by definition, like this symbol here, I'm summing the probabilities over an entire set, so I may as well just write it as P of A intersect B. It's another way of writing the same thing. So when you see P of A intersect B, what that really means is the sum of the probabilities of every individual omega in that set. Yes? Could we have used cardinality? Sure. Yeah. In fact, here's the equation. So the probability of A intersect B is 5, and the probability of B is 16. So you get 5/16. Now, okay. So this is the standard form that we use for the conditional probability of an event. The top part is the numerator. Even though it just looks like P, A intersect B, don't forget later, when you're operating at a more abstract level, that really what you're talking about is the sum of the unconditional probabilities of the members of this set, A intersect B. And then that we're rescaling that sum by the probability of the event P of B. And remember that the probability of any event is just the sum of the unconditional probabilities. Okay, so this equation, we've now shown it, we've derived it, we've reasoned through it, and you'll probably forget the definition over time, and it'll just end up being an atomic fact in your brain. Now, what I mentioned about the algebra thing is that I notice when I talk in office hours with students who like work on this for a while but don't get the foundations really down, is they start imagining there's some kind of interesting like magic thing that's happening where like if you have an and in the numerator and then you have a b in the denominator, then it turns into a line. And that kind of works often, but you can run into trouble if you start thinking about it only that way. If you forget about what's happening under the hood and turn it into an algebra of symbols that at intersections turn into bars when divided by a certain letter, you can run into trouble occasionally. Okay. This leads us to definition 14.1 from the notes, literally as they put it. They say, more precisely, for events A, B that are a subset, or not necessarily a strict subset, but a subset of our overall sample space, if they're in the same probability space, such that P of B is greater than 0, okay, so I didn't give that caveat before, but it's important so this doesn't blow up, then the conditional probability of A given B is the expression we just derived, and this is a super common expression you're going to use forever, ever and ever and ever and ever and ever. I mean, it's like when you start learning, I don't know, say machine learning, like this is just incredibly important to understand what's going on. Yeah, but don't forget what it really means. Yes? If P of B were 0 and you said P of A given B, then, I mean, I don't know, it just doesn't make sense. B can't happen, so, yeah. Maybe I'll do the Bertrand Russell, I'm God, I don't know. Okay, yeah. Okay, let's see an example of using this formula. And the rest of the day is pretty much using this formula. So suppose we're given an ace when we're playing some card game, and we want to know the chance that our next card will also be an ace. Okay, so here, let's say B is the event that the first card was an ace. That's the information you've given me. And then A is the event that the second card was an ace. Okay, so let's verify, just do the algebra and show that this is true, that the probability that the second card was an ace given the first card was an ace actually makes sense. Okay, so how does this work? So the probability that the first card was an ace is 4/52, because that's how many aces there are. The probability of A and B, that we got 2 aces, is going to be 12 over 52 times 51, because there's 52 times 51 ways of drawing 2 cards, and there's 4 times 3 equals 12 ways of getting 2 aces. Okay, this is the counting argument, just like we would have done in the previous lecture. And so the chance that our next card will be an ace, if we were to think about this right here, the chance that the second card is an ace, we can take this value here, 12 over 52 times 51, divided by 4/52, and get 3/51, and that matches what you expect. If you've taken an ace out of the deck, the chance your next one is going to be an ace is 3/51. Is this a good way to compute 3/51? No, it is very roundabout, but it's simply showing that, hey, it works in this case. Okay. As I know here, you can also just reason directly. In fact, that's the right way to figure this number out, but this is just showing, hey, yeah, it works like you might expect. Okay, so back to the, oh yeah, go ahead. Yes. Probability of B, which isn't, this probability of B has nothing to do with A. A might not even be defined, and you'd still be able to compute B. The probability of B is the unconditional probability of the event of B occurring. So whatever your original probability space was. So probability space is a sample space plus a probability function, right? And an event is just a set of points from that sample space. It's just you're just adding up all those probabilities under the original space. Yeah. Mm-hmm. Yeah. This is just the probability of B. Like this quantity in the denominator, you can compute even if A doesn't exist. Like given an event, if I tell you that this is the sample space, this is the probability function, and B is you rolled 6 dice and, you had 5 ones or something, then you can compute P of B. Hope that helps. I'm going to keep cruising though, sorry. Okay, so internet viewers, I'm going to go back to this example from the very beginning of lecture, and I want you to try and figure out that this is 44.4%, but I'm going to show you in this room how we can use this definition 14.1, that's this right here, to show the answer is 44.4%. Okay, so how do we do that? So first I'm going to say, what is the sample space? So the first thing I draw is whether I'm going to center 1 or center 2, and both of those things happen with 50% probability. Then in Center 1, there's 5 different restaurants that I could pick. What's the chance of any specific restaurant going to be? Well, 50? No, definitely not 50%. 20%, right? And so I say that all of them have a 20% chance conditioned on the fact that we pick C1, but the overall chance is just 1/10. The unconditional probability of picking this restaurant out of all the restaurants I could have chosen is 1/10, 10% chance, and these are 1/4. Okay, these are the unconditional probabilities. Okay. Conditioned on that I pick Center 1, yes, this is 20%, but unconditionally it's 10%. Okay, so these are all the probabilities of the individual outcomes unconditionally. All right, great. So then how do I compute the chance that I pick Center 1? Given that I ate at a Moroccan restaurant, well, I used definition 14.1, so I need to compute this numerator and this denominator. Okay, so let's start with, I guess, the numerator. What's the chance that we went to Center 1 and we ate at a Moroccan restaurant? Well, that's just 1/10 plus 1/10. That's the unconditional probability that I ate at one of these 2 restaurants. And then what's the chance I ate at any Moroccan restaurant? That's 1/10 plus 1/10 plus 1/4. If you work this out, you get 4/9, which is 44%. We'll see a different way to compute this later, but that's my speed round example of why this is useful. Okay. So again, these are the unconditional probabilities in here. Yeah.
So why was it 1/10 and not 1/10 for C1?
Why is this 1/10 here?
For those.
These are 1/10 because I want these to be the unconditional probabilities so that I can apply this formula. Basically, there's a set of things that can happen. There's 7 different restaurants I could eat at. And out of those 7, I hope you agree that the chance of eating at this one is 1/10. That's the way of thinking about it. Yeah? Or you can think about it as, what's the chance that you draw the tuple C1 and, well, I don't know. Never mind. Actually, I like it better. Just like, if you think about these 7 different draws. Yeah, this is 1/10, 1/10, 1/10. Okay? All right. And we're not going to get through, part of this is next lecture because this is notes 14. Okay. Let's talk about Bayes' rule. So Bayes' rule, or Bayesian inference in general, is a really powerful way to apply this definition to reason about the universe. The basic idea is you know something about the universe already, just from your prior knowledge, and now you're going to get new information, and you want to update your beliefs. That's the idea. So I want to update what I know based on my observations, and conditional probability is how I can do it. So what I'm going to imagine in this context is when I say probability of an event A, that's my prior probability. An example of this for the example we have today is like the chance that you have coronavirus. And when I say it's based on without any current observation, it's like background information. Like I know when I go to the website that like 1% of people right now have coronavirus in Berkeley. That's my prior probability about me, Josh Hugg, based on the population as a whole. Okay? Let's say I go collect some more information, B. So B is a current observation, an event like I put a stick in my nose and then I run it through a rapid test and it says positive. Now I want to know what's the chance I actually have coronavirus based on both of those pieces of information. I have the fact that 1% of people have coronavirus, and I also have the fact that I put the stick in my nose and the line came up red. And I want to try and say, okay, given those 2 facts, what should I believe? Now, the prior is important because let's imagine that you, sent a coronavirus test back in time to 2017, and someone swabbed their nose and they came up positive. You know the prior probability is extraordinarily low, probably 0, because it hadn't been released from RFK's lab or what. I don't know what the story is these days. But it wasn't out yet. And so that means even if it comes up, the prior probability tells you it's extremely unlikely that you have got the coronavirus in that universe. Okay? So we need both of these pieces of information. And I'm going to stop using colors blue and red for A and B because I need the colors for something else. Okay. So this is my coronavirus example I've been running with. And let's say, okay, A is I actually am a coronavirus person at this time, and B is the chance that I tested positive. I want to know what's the chance I'm actually positive given that I tested positive. Let's say we know the following. If you take the test and you are infected, it will be 90% of the time positive and 10% of the time negative. So it has 90% true positive rate and 10% false negative rate. Okay? So if you test positive, what's the chance that you're actually infected? Turns out we do not have enough information. Like this, the answer is not 90% because if you look carefully, the thing we're actually getting from the test, what we know about the test, I should say, is that the probability that you come up positive if you're infected, B given A, is 90%. And there's no particular reason to believe that P of A given B is the same as P of B given A. Back to my example of going back in time, right? Like it does, if you go back to 2017 and use the same test, it's going to be 0% chance you actually have coronavirus. There's no reason these two things here should be equal. Okay? But we do know that it's like a useful piece of information that it's a 95% chance of giving me a positive result if I'm actually infected, but it's not enough. So what else do we need to know? Okay, well, another thing we could know is what happens if you're not infected. So let's say if you're not infected and you have P of B given not A, okay, so you're not infected, maybe it comes up positive 20% of the time. This is much worse than an actual rapid test, but I made up this world where the tests aren't very good and is negative 80% of the time. This is still not enough information because we also need to know what the baseline prior is in order to do this kind of reasoning with this type of model. Okay? So let's imagine right now 1% of the people in town have coronavirus. Now with these three pieces of information, I can do, I guess I'll call it the reverse probability problem, kind of like figuring out what's the chance we went to Center 1 if we ate at the Moroccan restaurant. Here it's, if I test positive, what's the chance I actually have coronavirus? Okay. So if that happens, what's the chance you're actually infected? Turns out the answer, given the numbers I made up, is 4.4%, which might surprise you because the test sounds pretty good. I mean, it's 90% chance of being right if you are infected and only a 20% chance of being wrong if you're not infected. But overall, your actual chance of being positive is 4.4%. Okay? So let's see where that number comes from. It's just going to be algebra. It's a little bit of algebra hell, but I put a lot of color, so hopefully it's okay. So let's try and do this. Okay, so we know from definition 14.1 that the probability of A conditioned on B, this event A given on B, is the probability of A intersection B over P of B. And so we need to somehow compute those two quantities. We don't have them. In fact, they're colored in the color black, but we only have a green and a blue and a red number. So we need to compute these numbers in terms of our green, blue, or reds. We're going to start with P of A intersect B because that one's easier. So how do I get P of A intersect B from these numbers? Maybe try and foresee. Okay, we can use definition 14.1 again. We know that P of B given A is just P of A intersect B over P of A. This is where maybe doing the symbol algebra is actually helpful. Like if you bring the A over here, and A times a bar A becomes an A and B. And you end up with this expression here that if I know blue and green, I just move the green part over here, multiply both sides by P of A, and I get 0.009. So that is the probability of A and B. In other words, the probability that you are infected and you test positive is 0.009. So in all the universes where either of those things are, there's flips of coins for A and B, there's a 0.009 chance that both of them happen. Okay? So that's one of the two things we needed to know, is this numerator. What else do we need to know? The denominator, that's right, which is B. So P of B. That one's a little trickier, but also not so bad. More algebra gymnastics. This is the probability that you test positive. Not the probability you test positive given that you have coronavirus. This is just the probability you test positive at all. Okay? And that's assuming like you're a random person who has a 1% chance of having coronavirus and a 99% chance of not. So how do I do that? Well, I'm going to note that P of B, this is out of nowhere, but the probability of B is just the probability of A and B plus the probability of not A and B. Why? Here's a little diagram. Okay? So if we want to know the probability of B here, it's the probability that both things are true, that A is true and B is true. And it's also plus the probability that A is not true and B is true. Make sense? So I know that the probability of B is just the sum of these two little regions. These, unfortunately, are not our green or blue or red numbers, but we can get one of them. Let's see. So we know that, for example, that P of of not A and B is just going to be P of B right here. This is just the same old definition 14.1. This is just that same expression. This is definition 14.1. So again, like I'm making a couple moves. This is like watching someone play chess who knows how to play chess well or who typesetted the chess game in advance. So I basically deconstruct P of B into these two parts. Then I deconstruct this expression right here into this. This is one of my red numbers. What about P of A bar? Okay, where's that? How are we going to get this one? 1 minus the green number, so that's good. Okay, now we're getting closer. All right. And by the way, what about P of A and B? What's this one here? How do we get that? We already did it. That's right. Okay, so now we're just trying to get this one. So you actually already have that one. So now we're done because we have a green number and a red number. We plug them in and we get 0.198. And so this right here, this is just 0.009 plus 0.198, which is 0.207. Again, algebra hell. I'm a little sorry, but those are the moves that I made to get me there. If I actually plug in 0.207 into this denominator, assuming I didn't mess up the math, it's 0.044 or 4.4%. Okay. So this is something that doesn't really fit in your short-term memory super well, which is why we usually think of it as kind of just a simple rule, which I'll show you in equation form in a moment. But basically the idea here is even though the test has a 90% true positive rate and a 20% false positive rate, if we have a positive result, we only have a 4.4% chance of having coronavirus because the baseline prior drags us so far down. Okay? Yeah.
If we know that we're positive, like intuitively, why is known what percent of the region is positive and negative?
So this is helpful. The prior is important because if the prior thing is so extremely unlikely, like that you're the Kwisatz Haderach from Dune or something, right? Only one person gets to be that in all history. Then if you have like a test for it, even if the test is pretty good, the baseline chance is just so low, if that makes sense, intuitively. Right, like the test is, yes, it has these good rates, but the thing is, like if it shows up positive, it's more likely that the test is wrong than that this extremely unlikely thing is true. It's the condition is very rare. A is very rare in this case, yeah. We could also do this entirely symbolically without plugging in the numbers for algebra hell. This is like extra algebra hell. If I wanted to know the chance I actually have coronavirus if I test positive, I could say, okay, definition 14.1 gives me this expression, then definition 14.1 gives me this expression, then I can take PB and split it into two pieces. This is exactly what we did before. Then we realized this one we can also just replace it by P of B given A times P of A. This one right here is where we did definition 14.1 again. That gave us our red number. And then this one we got by doing 1 minus the green number. Okay, so that's the long version of this. And again, this is like eye-watering, watching a whole bunch of algebra. But this is where we get to, I guess, the short version of this equation, which is that often people just write it like this. The probability of A given B is the probability of B given A times the probability of A over the probability of B. That's the very short version of it. And if you want to actually know what the probability of B is, yes, you can expand it out into this bottom denominator. Okay? And so if you wanted to, you can plug in all the numbers just as we did before and get 0.044. So when you're doing this kind of reasoning, often you've just memorized these two formulas. That this is Bayes' rule over here, and the bottom one is known as the total probability rule, or law of total probability, which basically says you just have to consider, I don't want to say action. This is what it says. Okay. So those are the two rules that people often memorize individually rather than working through all the algebra over and over. Okay. All right. Okay. Let's see an application. Hey, remember these shopping centers? Well, let's suppose we want to find the probability we ate. What's the probability? Sorry. Let's first showcase the total probability rule. I'm going to do that one first. So the total probability rule we could use to tell us what the chance is that we eat at a Moroccan restaurant in the first place. Okay, so if it's the same exact problem, same numbers, what's the chance that we eat at a Moroccan restaurant if this is the way that we choose? Okay. Looking at you, people pausing the video. Okay. So we're just applying the total probability rule. We say there's two things that could happen. Either we pick center 1 or we pick center 2. In the coronavirus example, it was either we test positive or we don't test positive. If we pick center 1, the chance we pick a Moroccan restaurant is 0.4. If we pick center 2, the chance we pick a Moroccan restaurant is 50%. Therefore, the total chance that we pick a Moroccan restaurant is 45%. So it's like two different ways I can go. Okay, and then among those two choices, I figure out my weight for the or figure out what the chances I had a Moroccan restaurant, and then I'm just weighting it by the chance that I picked whichever center. So the total probability rule, despite all of that backbending and algebra and like, oh, I'm so clever, look at all this typesetting, it's just this. That denominator, it's like very intuitive when it's not turned into symbols, and we have a nice concrete example to look at. In other words, the thing we just did, which hopefully feels very intuitive, is actually this big algebra hell at the bottom. Okay? Right? Okay, so how do we solve this right here using Bayes' rule? I said Bayes' rule is this expression. So to solve this, the tricky part was finding the total probability of a Moroccan restaurant, which was 45%. What's P of C1? 50%. What's the probability of picking a Moroccan restaurant if I'm at C1? 40%, right? That's it. So 40 times 50 over 0.45 gives me 4/9. So this is a nicer way of solving the problem. And once you're adept at this, this is the way you would do it. Okay? So we did it two different ways. One involving a lot of conditional probability futzing. The other one is to kind of pre-cache or have nice expressions that we can just plug right in without thinking very hard, and you get 4/9. Okay. We're racing along. Okay. Any questions about this? Yeah. Yes, I'll talk about 3 shopping centers in just a moment. Good question. Okay. So let's say we have 3 shopping centers. All right. So now I have 3. So to handle such situations, what we'll do is imagine what we'll call a partition of an event. And here I'm only going to kind of touch on the high-level picture. The notes cover it in a little more detail. It doesn't generalize in any particularly super interesting way. I think the partition is the most interesting part. But basically, let's imagine we have an event A, which is partitioned into a bunch of different events. And when I say an event is partitioned, we mean we have some rules, which is that all those events, if you union them, you get the original event back together. And that if you union any particular... nope, that doesn't make sense. That should be a cap. Okay. If I look at the intersection of any 2, then the intersection is 0. They're mutually exclusive events. So above we have 3 events, 1 for each shopping center. Okay, enable. And so our total probability rule before, we had 2 different choices, was as follows. So we had, if we have 2 different events, A and, yes, if we have 2 different events, A and not A, then we can use total probability. We can write total probability like this. If we instead have many different choices, 3 different shopping centers, for example, that are partitioning the sample space, then the total probability rule looks like this. The probability of B is going to be the sum of B intersect AI. That'll work just fine. Now, these don't look like the same formula, but I claim that this top one is just the same thing as the bottom formula. How does that make sense? Like, what am I partitioning up here? This is subtle, yeah? Yeah, A and A complement. So originally I was partitioning the entire sample space into 2 events. A1 is A, and A2 is A bar. So if you think about it that way, that's the natural generalization. Okay? We don't use this super often in CS70 at least, but that's the idea. That the way you generalize this pattern to having multiple conditions other than just testing positive or testing negative on a test is as follows. You have the entire sample space, and you break it into mutually disjoint, or into disjoint subsets, each of which is an event which partitions the space. Okay? You can also write this using definition 14.1 as follows. All I'm doing is just taking each of these and turning it into its broken apart version. Okay? And then Bayes' rule, if you want to consider not just the denominator, the total probability rule, if you have your space partitioned into A1 through AN, then Bayes' rule is as follows. The probability of A given B is this expression here. And again, you can use P of B as that total probability rule from the previous slide. But I just wanted to briefly touch on this, and I'm glad you asked, so it motivated it. But we're not going to say much more about it. Okay? Don't want to read those bullet points. Okay. So that's how you generalize beyond 2 events for Bayes. Yes? P of AI given B. Which one? AI given B. Yes, thank you. Yeah. Okay. I do want to talk about independence before we get there. And I think that generalized Bayes is not the most important topic in the notes. So I do want to talk about independence. Okay. So earlier, sorry about the typesetting here. Earlier we talked about how the probability of two events is sometimes the product of their individual probabilities. So for example, if we roll a four-sided die twice, where the probability of 1 is 5/8, we know, let's say that A1 is the event that the first die is 1. In that case, we know that the probability of A1 is going to be 5/8. Okay? Let's say A2 is the event that the second die is a 1. And we know also that the probability of A2 is 5/8. Okay? Now, earlier we said that the probability of both events happening, just when we were doing this in the previous lecture, of getting A1 and A2, you'll get 5/8 times 5/8 equals 25/64. The probabilities multiplied nicely because we had these two different dice rolls that were independent. Okay? So the outcome of each roll doesn't affect the other roll in any way. Now we'll say just formally that two events are independent if that property holds. If the probability of both of them happening is the product of their individual probabilities, then they're called, that's independence. Let's think about what happens if events are independent and we consider the conditional probability. Okay, so what's the probability of A given B if, let's say they're independent? Well, we can rewrite P of A given B using definition 14.1 as follows. That's our usual thing. P of A intersection B is the product here by definition. That says they're independent. What happens here? We end up with just P of A. The P of B's cancel out. So in other words, knowing that B occurred is useless. Like P of A given B is the same as P of A. You get no additional information from an independent event. If I roll two independent dice rolls and you say mine was a 3, that doesn't affect me. Okay? Knowing B tells us nothing about A. All right. We can also define what it means to be mutually independent. So let's say we have 3 events, A1, A2, and A3. So these events will be called mutually independent if all of these are true. So the probability of any pair happening is the same as the product of the probabilities of each of the individual events. Then we have this version, which is 3 different things. So the probability of all 3 happening is the product of their individual probabilities. And so I want you to think about this question, as I guess this will be my actual last one probably. So let's imagine we flip a fair coin twice. And we'll define these events that A1, the first flip is heads, A2, the second flip is heads, and A3, both flips are the same. So my questions for you are these events pairwise independent, these top 3 constraints, and are they mutually independent? Good luck. Another way to think about this is, does knowing anything about one of them tell you about any of the others? Or does knowing some combination tell you about any of the others? All right, let's go through the combinations. If I know the first flip is heads, and that's like if I know the first flip is heads, does that tell me about anything about whether the second flip is heads? No. Does it tell me anything about whether both flips are the same if all I know is that the first flip is heads? No, that seems fine. Okay, similar argument for 2. Like 2 doesn't tell me anything about 1 or 3. How about if I know that both flips are the same? Does that tell me anything about whether the first 2, or does it tell me anything about whether the first flip is heads? No. If all I know. Okay, are all of them together mutually independent though? No. Why? If A1 and A2 are true, the probability of A3 is 1. Right. Yeah. So if you know A1 and A2, then you know that A3 is also true. Right. So they are pairwise independent, but they are not mutually independent. In other words, the probability of A3 given the A1 and A2, that's what you're saying, is just going to be 1, which is not the product that you would expect if they were independent. Okay. All right. We can expand our definition of mutually independent. So for 4 events, we would have 11 constraints. We have these 6 pairwise constraints. We have 4 3-way constraints, and we have 1 4-way constraint. That's a natural definition for mutually independent, and we could just keep going. So for n events, we would have 2 to the n minus 1 constraints. There'd be n choose 2 pairwise, right? We have n choose 3 3-way constraints, n choose 4 4-way constraints, and so forth. And we could actually represent this with a more compact notation. I think a nicer notation than the one in the notes personally is, let's say I'm just going to define that as the set of all subsets of 1 through n. And we're going to have to require that I has at least size 2 because we want to talk only about pairwise and so forth constraints. I can say that if we have mutually independent events, the probability of getting the intersection of these different events, AI, where and we consider all of the, we're considering all possible subsets that are at least size 2. Then we have that the probability of that intersection is going to be the product of all the individual probabilities. Okay, they give definition 14.5, which is fine, but I like this one slightly more. It represents the same idea. Okay. All right, I have one more thing I think I want for you today, which is the product rule. So in engineering, we often care when we're building systems about the probability of the intersection or unions of events. So for example, if you're landing a rocket and trying to catch it, there's a lot of stuff that has to go right. And your chance of success is going to be the probability that every single one of them goes right and that you manage to actually catch your rocket, which in this case you've probably seen was successful. So this is pretty outstanding to be able to do in general. And so I want to talk about this expression. It's a very common real-world expression. We want to know the probability we get intersections. Okay? So let's say we want to compute the probability of intersections, but they're not independent. If they're independent, it's fine. They just multiply the individual probabilities, but we can't just multiply the probabilities if they're not event. So for example, the event that 2 coin flips are both heads, and the probability that the first coin is heads, the probability of the intersection of that is not 1/4 times a half. You can't just multiply these 2 probabilities, because if it's both heads, you already know that the first coin is heads. Now, if there's only 2 events, which we'll start with, we can take advantage of our definition of conditional probability, and we can say that the probability of A intersect B is just the probability of A times the probability of B given A, right? So if we want to know just like what's the chance that, I don't know, the rocket doesn't explode on the ground for whatever reason, and also it gets above the ground, then we can use this expression. And it's true even if there's dependence between these 2. Okay? So for the coin example above, the probability of A given B is just 1/4 times 1. And the reason this is 1 is because if we know that the both are heads, then the first coin being heads is definitely 1. Okay? So I think we'll wrap up maybe on this slide, which is, what do you think the next term is if I just keep going? Like imagine I have n events, and I say, okay, so I got A1, and maybe I have 3 events or 4 events. What do you think the next term is going to be? We know that this one works based on the probability rule. I want you to try and speculate here, and then what I'll do in the next lecture is I'll prove that the thing you're coming up with is correct. So give yourself a chance. Just kind of guess what you think is next intuitively. And if it helps, you can remember that this thing is just the probability of A1 and A2, just these first 2. Okay, all right, I'll tell you what I came up with. Okay, so the next term, I mean, maybe you came up with this, that the probability, the next term in this product is going to be the probability of A3 given A1 intersect A2. And the reason, one argument for this, or an argument for this, is that we know that the product of these first 2 things is just the intersection of A1 and A2. And so what that means is if you actually multiply this thing out, you'll end up with the following. Like, the probability of A1 intersect A2 times probability of A3 given A1 intersect A2 is just this probability. So what we'll do at the beginning of next time is we'll prove that this holds, and then we'll also talk about unions of events, and then we'll talk about some applications of all this stuff. So the next lecture is only going to have one new set of definitions, which is about probabilities of unions of events. And then from there, it's going to be a bunch of just exercises with this to reinforce all this tricky stuff that we're learning. Thank you, everybody. I'll happily take some questions.